Okay, this video is talking about turbines, and I want to look at an air turbine. I'm going to assume for the air that Cp equals approximately 0.25 BTUs per pound degree Fahrenheit. BTUs per pound degree Fahrenheit. And first I want to draw a turbine and kind of explain what goes on in it. Let's suppose we have a turbine. Turbine is an expanding, allows room for the gas to expand. Starts with some small blades. The gas comes in at high pressure and high temperature. So let's put it into this particular turbine at 150 psi. And let's make the temperature 1000 Fahrenheit. So coming in at 1000 Fahrenheit and 150 psi, going through this turbine, it's very dense gas because it's high pressure. As you go through the turbine, the blades spread out. You call these stages of the turbine. And so what you do is you allow for the gas to expand so that the velocity doesn't raise too much, although the velocity will frequently increase. And so though we may have negligible velocity coming in, we're going to design it such that the velocity coming out is approximately 100 feet per second. 100 feet per second. So 100 feet per second coming out of the turbine. Now those blades are attached to a steel shaft, and the steel shaft is going to go down through the middle of the turbine. Blades are attached to it, and that shaft will be connected to a generator or some kind of pulley or some means to gearing mechanism, some means to export work. So we got W dot coming out of the turbine. And suppose that we want to make this work out of the turbine 50,000 BTUs per second. 50,000 BTUs per second, by the way, comes out to about 71,000 horsepower or 53 megawatts. And just to put it in perspective, it takes a Boeing 747 about 90 megawatts of power to get off the ground. So it seems like a lot of power, and it is, but give you an idea of the size of this thing. Now let's suppose that the temperature coming out of the turbine is 400 degrees Fahrenheit, and that the pressure coming out has dropped down to near atmospheric, or about 15 psi. 15 psi coming out, 150 psi coming in, and it dropped in temperature from 1000 degrees to 400 degrees. Let's first of all, I want to introduce this idea of kinetic energy per mass. So let's calculate that coming out of the turbine, kinetic energy per mass, and we'll call that KE bar. Put a little bar over that to indicate it's per pound, is equal to 1/2 V squared. 1/2 V squared. And that comes out to 1/2 times 100 squared, feet squared per second squared. And let's divide that by 32.2. Get it into new units. Pound mass, feet per second squared per pound force. I'll put the pound force up here. Now I'm going to divide that whole thing, by 778, and there's 778 foot-pound force per BTU. And so when we're all done canceling the units, and I would suggest you stop here and check your units, When we're all done canceling the units, that comes out to approximately this kinetic energy per mass, 0.4 BTUs per pound. Okay. Okay, cleaning it up a little bit, we have 0.4 BTUs per pound as the kinetic energy leaving the turbine. So now we can do the mass or the energy balance on the turbine. Let's write it EB. And that will be N, which is M1 or M dot of the air, times H1. There's no kinetic energy coming in, or we're neglecting it. Very small velocity coming in. M dot H1 equals M dot of the air. And we look at the energy out, H2 plus kinetic energy per mass, call it KE bar at 2. And now I'm going to assume that in addition to that, maybe we have a little bit of heat leaking. Suppose that for every pound that goes through this turbine, we lose heat in the amount of 10 BTUs per pound. That would be the equivalent of dropping about 40 degrees and not getting any benefit for that. So this would look like, suppose that it's not very insulated, not very well insulated over in some part of the turbine, and you have a heat leak. Draw that as red. Usually heat leaks out of a turbine because they'll be operating at elevated temperatures. So suppose we had some sort of heat leak, Q bar, and for every pound that goes through there we lose 10 BTUs, so we'll make Q bar equal to 10 BTUs per pound. So we have the heat mass flowing in with the H, mass flowing out with its H and its kinetic energy, and we also have a heat leak which we're going to express as 10 BTUs per pound of air that goes through the turbine. All that is going out, but we also have the work leaving the turbine, and so the work leaving the turbine, we'll say W dot out of the turbine. Putting the numbers in, we have, and rearranging a little bit, we have M dot air times H1 minus H2 minus KE2 minus the heat that's lost, Q bar, let's call it, and all that's going to add up to, when we take that and get our balance, we have the work, which is the work which comes out to 50,000 BTUs per second. Okay, so plugging in, what do we know about H1 minus H2? H minus 1 minus H2 is Cp delta T, treating it as an ideal gas, so that would be Cp times T1 minus T2 minus kinetic energy, which we said was 0.4, minus the 10 BTUs per pound that we dropped from our heat. Cp will take to be 0.25 over that temperature range for air. That's about right. T1 is 1,000. T2 is 400. Minus 10.4. All that comes out to the 25,000. All that is multiplied by our mass flow. So we can solve for the mass flow of the air going through this turbine, and it tells us that we have to supply air at a rate of 358 pound mass of air per second. That's a lot of air. So our question might be, what's the size of this thing? What's the size of the exhaust port in order to let it go out at 100 feet per second? Obviously, the faster it goes out, the smaller the exhaust port we need. So we're limiting it to 100 feet per second. So the question is, what size exhaust port would we have here? We solved one problem, and that's to find the amount of air we need to supply to produce this 50,000 BTUs per second. Now let's find out what size exhaust port we'll need. Again, cleaning up a little bit, give ourselves some room to work. We have the continuity equation, which says that the mass flow over the molecular weight, RT over P, is equal to the volume flow. And we know that the volume flow has to be equal to the cross-sectional area at the exhaust times the velocity at the exhaust. So we can solve this for the cross-sectional area. The area is equal to m dot RT over molecular weight. See, molecular weight of air times P times the velocity in the denominator. And that comes out to, plugging our numbers in, we have, let's see, 358. R is going to be 10.73, you recall. In English units, that's psi feet cubed per pound mole degree Rankine. 10.73. T, you've got to be careful with. T I gave you in Fahrenheit. And recall that was 400 degrees Fahrenheit, so we have to put 400 plus 460 to get it in degrees Rankine. Divide that through by the molecular weight, 29 for air, pounds per pound mole. P is 15 psi, and the velocity is 100. Velocity feet per second. All that comes out to a cross-sectional area of 75, or about, really actually about 76 feet squared. Take the square root of that and you got a little under 9 feet, so about a 9 by 9, a little under a 9 by 9 foot squared opening. So that's a fairly large opening, about the size of a small garage door. So let's just recap a little bit. We're looking at turbines, and the way a turbine works is you put in very high pressure gas, and as the gas expands, its velocity starts to go up and it's impinging against these blades. What you try to do, the reason you're increasing that, is you don't want to have too much of a difference of the velocity of the gas compared to the velocity of the blade, because the thing is, if you have a high difference in velocity of the gas to the velocity of the blade, then the gas will have some friction as it slides across the blade, and friction creates irreversibilities. Let's call it dissipation of what we're trying to convert good mechanical energy into frictional energy, which then winds up as heat. So you wind up with this heat term coming out down here and lose some of your potential. Also, the heat can go into the gas itself, and you'll wind up with gas leaving hotter than it would otherwise if we try to run this turbine as efficiently as possible. And again, as efficiently as possible involves having very low gradient, let's say, between the velocity of the gas itself and the velocity of the machine that it's turning. So that's a little introduction to turbines, and this is a gas turbine. Steam turbines operate similarly, but the thing about steam is it could, as it goes through this turbine and starts to drop in its pressure, it can get down to a range where liquid will start to form, and that can be a little bit of problem if you have little drops of liquid hitting these blades. But that's an issue. We'll look at that in another topic.